Okay, so this is week 2, class 2, and we're still talking about chapter 2 in residential energy book. We covered in the last, I'm going to go over the material from last class just to recap, to make sure we understand what's going on. So we said thermodynamics is the branch of physics that concerns with the movement of heat from one place to another and the work done by heat. And can somebody remind me what is the first law of thermodynamics?
Either created or destroyed.
Okay, yeah. Conservation of energy. Heat does not get destroyed or come from nothing. Everybody have a question about that? Okay. Second law of thermodynamics. Connor? Don't look. Yeah? If you want to do it the opposite way, you have to put in some work. So I'm going to write it down. Simplify thermodynamics. Conservation of energy. Second law. Heat Okay. So with those two principles, you can think about residential energy, and you can think also about cooling and heating with a lot of good basics. So we talked about that. We talked about, again, how energy transforms from one form to another. We talked about first law, forms of energy, one form to another. Units, we talked about BTUs, terms. I would say BTU is the amount of energy in one stick match, not stick. And it's also the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. This is what we need to use, BTUs and terms, and sometimes we will use horsepower. And we say thermodynamics is the branch of physics that deals with heat and movement of heat from one form to another. Circle of energy. And again, second law. So when anybody want to think about the second law, think of an air conditioner. We're actually pumping heat from cold to hot, relatively speaking, and we're putting a lot of work in the form of electricity. Electricity is turning on a motor, the motor is turning on a compressor, the compressor is doing some work into changing the volume of gases, mainly refrigerant, to move that heat. We talked about that as well. We talked also about temperature and heat, how heat can be measured by temperature. But what kind of heat is that? That's what we're going to talk about in this class. There are sensible heat. So sensible heat, you can sense it and you can measure it with a thermometer. Latent heat, you cannot. So that's what we want to talk about, which is sensible and latent heat. So sensible heat, you can put a thermometer and measure the temperature. So if you feel something that's hot, that's sensible. What about the other type of heat, the latent heat? That's the heat, I'm gonna write down if I have it. The energy put into substance to change its form. It's a form changing heat. So, if I bring a pot full of ice, crushed ice, and I keep heating it, until the ice completely melt into water, the temperature in the thermometer will be what? 32 or 0 Celsius. Because all the heat I'm putting into the pot is changing into, is used to change the phase. So you understand that solids has more bonds between the molecules, right? And liquids have less bonds, more fluid bonds. And gases have less bonds. So this energy put into the substance is used to break down those bonds. And therefore, the temperature of the molecules are not increased. Question?
How do you tell how close you are to reaching that 5 times the total amount that you need to get it to change states? If you're halfway there or 3/4 way?
You can't tell. You can measure the energy you put into it, but you can't tell.
There's no way to tell by pressure or anything? There's no
No,
change?
not really. You have to just observe and see how much of the substance is left. Especially if you're stirring it. It will take a while for it to change phase. And I do this experiment in the prism of refrigeration course where I bring a pot with ice actually, and I put a thermocouple on it and keep heating it. And I do the calculation to tell you how much energy I have to put into it to make it melt. So there's energy, I think I forgot the number, a certain amount of energy to melt 1 pound of ice, a certain amount of energy to evaporate 1 pound or 1 gallon of water. So if we can remember that latent heat is the energy used to change phase, either from solid to liquid, liquid to gas. And the temperature does not change. So again, going back to the example, I think I have a picture here. Yeah. Boiling and freezing. So I put a thermometer in a pot of water full of crushed ice. I turn on the heat. The thermometer will still show 32 until the complete ice turn into water. Then we'll start seeing an incline in temperature from 32 all the way to what? 212 at atmospheric pressure. Then what happens? It stops. It stops. I'm putting more energy, but no increase in the temperature on the thermometer. We start having steam. Steam will come up, it will evaporate until it will remain at 212 until the complete water is gone. So that is latent heat. And that's a very major thing that we use for refrigerant. Refrigerant does boil at lower temperature. We use boiling and condensing to move heat from one place to another. So this idea was very attractive to a lot of scientists. Okay, how can we use this little mechanism to transfer heat from one place to another? And they used the concept of chillers for a while. And if you think of people who live in Africa or the North Africa or the Middle East, and it's really hot at night, what do? They do what they call Egyptian bed. Basically, you wet the sheets. You wet some sheets and you just cover your body with wet sheets. What's happening? It will cool your body because the water needs some heat to evaporate, and it will absorb some heat from your body and evaporate and cool you off. We have these concepts in so many ways in our daily life that we are not aware of. So you wet things, and as they evaporate, they cool off the atmosphere. If you go to some restaurants and bars that have outdoor seating in hot climates, they have misters, right? And those misters actually, they atomize the water to small particles that will evaporate easier, and the air will come as very, very cool, even though there is no refrigeration cycle going on. What's happening is the water evaporates, and as the water evaporates, it absorbs some heat, and that will lower the temperature of the air. Question?
Is there a temperature where the whole inside of the boiler would experience like the leading frost effect around the outside of it?
Say that again?
That hot, the leading frost effect, where it's boiling and it's got a surface of steam around the whole area, so it's transferring right through into the water?
Yeah, that does happen in some industrial boilers. That does happen. It depends on the boiler configuration, but I think they worked around us in aligning the tubes inside the boiler. But I want you to keep thinking about the conversion of heat from one substance to another. And I talked about, we'll talk about the mass inertia, the heat inertia, and how objects stores heat. And water is one of the best element to hold and store water. It has really store heat. It has very good heat capacity. Sometimes now they fill bricks with wax. The wax will melt during the day and absorb heat and release that heat during the night to keep your house cold. So that's something you can think about for phase change, how you can melt things and freeze them again to store heat. It's a storage of heat and releasing of heat over time. And that's the basis for latent heat. Again, we go back to enthalpy, which is the amount of energy that we can, the amount of useful energy in a substance that we can use for material. And as we heat steam, it has more energy because we're putting some energy into it. So we can have superheated steam. Superheated steam can turn turbines. Superheated steam is what generates electricity now. We generate electricity now using coal and fuel oil by heating water and generating steam at high pressure that will push a big wheel. This big wheel is a turbine, and that turbine will turn a generator and make electricity. So there's a lot of energy in steam. And if we look at this little chart between 32 and 212, we'll see that the enthalpy, which is the amount of energy per pound, changes from 0 BTU per pound at freezing because it's solid now. It has no energy in it. You cannot do anything with it. So 0 BTU per pound. As it gets hotter, it has more energy, useful energy that we can use for something, to heat something else, to melt something else, or to move something. And we go to 212, which is the regular steam, not pressurized steam, and that's around 1200 BTU per pound. Then we can go to superheated steam. Where we can pressurize the steam and can be up to 500 megapascal or 5 bars. That's what we use for big generator. I'm sure Bill or Tom Therian will take you to a power plant and you will see a huge generator that uses steam. So they use fuel oil to heat steam at really, really high pressure. So steam has a lot of power. If you heat air, it does not have any energy, any moving power in it. And that was the basis of the steam engine. We realized that when we heat water, the steam has a lot of energy in it and power and can push through physically, mechanically, some either a big wheel of a turbine or a piston. So, and that's how we calculate enthalpy. There are other materials that we also can use to push through some, but it's not. It has different application. And these materials are similar to refrigerant. So we always use refrigerant, and we want to manipulate refrigerant to have it boil at lower temperature and condense at higher temperature to be able to move heat easily from one place to another without reaching this high boiling or cooling. Okay, so we talked about energy. We say that energy is mostly from the sun and transformed from one form to another, from chemical to heat, from heat to dynamic, from dynamic to mechanical, from mechanical to electricity. So it just changes. We talked about the science of thermodynamics, which is the physics of heat movement. First law, second law. We talked about sensible and latent heat. We talked about enthalpy. Any questions about that? I mean, we do not have to understand the entire physics of it, but we can understand the gist of it and what does it mean, what is it related to. Nobody will come into you as a technician and ask you, hey, well, define the first law. I don't want you to define it. I want you just to understand the concept of that. That if you burn some fuel in the basement, you want to understand where did it go, where did the heat go. I'm burning 3 gallons of fuel and I'm getting no heat. So it must have been going somewhere. And you have to understand the amount of acceptable losses, whether in the boiler, in the duct, in the system, and that can help a little bit. And also you want to understand the efficiency of an air conditioner if you're putting if it consumes a lot of energy, however, it's not producing enough cold air. What does that mean? That means something is wrong with the AC. There's some kind of loss of efficiencies, and you have realized that newer air conditioners are way much efficient than older ones because of these little losses. People became more and more aware with these losses and try to reduce them. Of course, it's almost impossible to get 100% efficient equipment. You can aim close to it, but there's always some kind of losses. And there are some losses you cannot go around. And one of them is the entropy factor. I'm not going to talk about that a lot, but entropy is the chaos of material that we cannot account for. That there are some losses called isentropic losses for turbines, which means no matter what you do, you're not going to get 100%. There's always small amount of losses. And if you work in a power plant, probably you'll think about that. So what are we going to talk about now? Energy and power, heat and work, pressure versus flow, energy transformation, energy transport, types of heat flow. These concepts are very, very important to solidify and understand, to be able to go into residential energy with good awareness. So can somebody tell me what is the difference between energy and power? So if I have a gallon of fuel, that's energy, right? Right?
Hours of work that energy is doing.
Energy is potential.
Okay. What else? Huh? Okay. Close. What else? Think about your car. You have a Corolla and you have a Ferrari. They use the same energy, right? Say they use the same fuel. They both use gasoline. Oh, sorry, maybe the Ferrari uses a higher fuel.
Yeah.
Think of a Lexus and a Corolla. They use the same amount of energy, right? Same gasoline, but which has more power? Lexus. So what is the power? Huh? How do we buy that?
The conversion of energy.
The amount.
Okay. Okay.
Whatever can use the energy the best.
Okay.
Most efficient.
Good. And a factor of what?
The amount of energy it uses.
Per time. So the time. So when you go in a drag race or buy a powerful car, what do they tell you? Tell us the horsepower. This is how much this car will go from 0 to 60. This is your power. So power has to do, this is energy over time. The energy is the same thing, but how fast I can consume it and how efficient, as you guys said, it's all correct. How do we utilize this energy? So energy is a quantity, and power is this quantity over time. So you get a motorcycle, and it uses fuel, same as the car, but the power that it consumes the energy is a factor, which is the mile per gallon again. So how fast do you use this energy, and how much power you get out of it? You need less power, you need more power. So power is a factor of energy over time. Okay? So example for in our field for oil burners, you have an oil burner, they all use oil, the same energy oil, correct? However, some of them have 1 gallon per hour consumption, some of them have half a gallon per hour, and 2 gallons per hour. So this consumption, if you think about it, what is the factor of the time? How much I'm burning per time, and how much power I'm getting out of it. Heat and work. So work mostly is defined by displacement. If you move one thing from one place to another, the distance is considered work. And your car is doing some work, there's a lot of displacement into the engine. And if you know about cars, probably they will tell you this engine has this much piston displacement. And in Europe, they size the engine not by horsepower, but to what? CC? Yeah. Displacement, CC. And this is how much you are doing displacement and work inside this engine. And heat is measured in BTU, and again, it's either sensible or latent heat. Think about these here. So energy is a quantity, power is energy per time. And think of the piece of coal, that's energy. How fast you burn it is up to you. Gallon of fuel oil can be burned over an hour, half an hour. You get a lot of heat, small lot of heat, you can make it last longer. And think of also fuel consumption for your car. That's energy and heat. So car, horsepower and torque. Horsepower enables you to go faster and consume more gas, and depending on how efficient the engine is, but again, more power also means more energy. Again, nothing will come out of nothing. It's gonna come at a cost. You can be fancy and have an engine that burns the fuel efficiently. You can have a turbocharge that can make you use the fuel more efficiently. And we said the car engine efficiency is 35%. So you can come with some creative ideas and make it a little bit better. There's, I think some scientists here in Mass that are working on something on the engine called the Miller effect, which can make the engine much efficient, up to like 50 or 60%, the gasoline engine. But anyways, torque, what is torque?
The energy being thrusted.
Anybody have a truck?
Twisting.
Twisting power, yeah. It's a twisting force. So when you buy a truck, you always worry about the twisting force. Is this car gonna crap on me in a hill? Is it gonna be able to carry stuff upward? So that is torque. So when you buy a car, they always tell you horsepower, mostly for speed, and how fast can you go from 0 to 60. But torque is the twisting power, how much force do you have, and it's very related to the size of the piston and the size of the engine that can push against the crankshaft. Work and heat. Work needs displacement and movement. We have to displace something from one place to another. Power produces work or heat. So power can be just heat. When we burn oil, you get heat. And we can also use power to move things. We can use this heat to push on a wheel or turn on a motor. So pressure and flow. That's something we have to think about a lot because we're going to be doing a lot of pump sizing. We'll do a lot of water flow through pipes. We're going to have flow of air around duct. So we got to think of this concept a little bit. Flow, water in a pipe, current in a wire, heat through substance. This is flow. So when we think of flow, it's the movement over time of this fluid. So fluid means either liquid or gas, right? They're all fluid, they all flow. Fluid buildup is pressure. And Tim was talking about that in the previous class. It's like you have, actually John also, when you have a hose and you choke the hose a little bit, or put a nozzle in, you're building a lot of pressure back up. So that's pressure. So you got the pressure and flow, they come together, and based on the speed of the current that goes, we can build more pressure or less pressure. So if you have the same water pressure in your house, would a big faucet have more pressure or less pressure than a small faucet? Less. So bigger, easier path for the water to go, less pressure. High pressure, small resistance. So flow buildup is pressure. Flow leads to equilibrium and no pressure. Think of flowing into a balloon. You're putting a lot of pressure to a small orifice, and it gets bigger and it builds up a lot of pressure because there's a lot of resistance. Any questions about flow and pressure? Whatever analogy you can have to make you understand the idea, whether it's water, whether it's air, just think of pressure and think of flow. I will put some kind of physics to it somehow to understand it, because we will need to do that for at least when we do piping and when we do pump sizing. Energy again, transformation and transport. Why do I want to talk about this more and more? Because again, we have to think about the energy that we are making in our house. So usually when you have a boiler or a furnace, where is it located? The basement, sometimes the attic. So this is your source of energy. Where do you want this energy? In your living room, in your bedroom. So you're gonna transport that energy from there, from the boiler all the way to your bedroom. And how are we gonna do that? So we are going to transfer that from, first of all, we're gonna buy either wood or oil to make that heat. So we transform energy from one form to another. Then we have to transport that from the basement the room. And again, the better efficiency we have, the more we can transfer that and less losses. Think about again, the car's hydrocarbon does not move anything, but the heat does. The idea of combustion. Somebody realized that when we burn something, the gases get expanded. So okay, we put that in a piston and use that to be a sealed piston, so it will push back. And this is how we got with the idea to use a steam engine and then the internal combustion engine. So we transfer energy from hydrocarbon chemical energy to heat to mechanical. Transport, we have the mechanical part in a piston. The piston moves the shaft goes to the transmission goes to the axles and goes to the wheel. So can you think why this will be very inefficient? More parts, more losses. Every time you go through one of those parts, you lose more. So you lose a lot of energy in the piston because you're not using all the heat. Heat they're going to the radiator, and that's a loss. When you go to the shaft, there are some losses between the gears or the connections. Then you go to the transmission, and there's a lot of losses in there. And the proof that there is losses because there is heat. So you're gonna have a lot of losses, and it's getting better over time. And you go to the axles, and you go to the wheels, and they are all combined into a lot of losses to be able to get the car going more efficiently. Did you ever notice that all-wheel drive cars are more have more fuel consumption than regular cars? Why? Losses. So many wheels running all the time, so many gears. So in a Subaru Impreza, you get like 24 gallons, which is the same size as a Civic. Civic gets 40. This one gets like 24. So all these gears are running all the time. This is all losses. If you drive a stick shift, usually a stick shift is more efficient than transmission. Why?
Power in the clutch on an automatic.
The viscous coupling.
Yeah.
The coupler is running all the time. It will make you lose 1 gallon per 1 mile per gallon for each turn. It depends. And that's why when you have an electric car, they say the car is 95% efficient. No more connections. 4 motors in each wheel, electricity, motor turning. No transmission, no axles, nothing. So that's the whole argument and how the whole thing kind of made sense. I'm cutting off all these mechanical parts, and the more parts you have, the less reliable the equipment is. The more possibility of failure. So the least part you want, the better. We took a course in quality, and that's what our objective is: to make an equipment with so many parts with least parts available. The more parts you have, the more possibility for failure. This is possible in some things and not possible in others. But you try to reduce the amount of moving parts and the amount of parts in the equipment. It's so the more you can think about it this way, the better. And if you think of the current ACs, they got rid of a lot of things that they used to have in the past. A lot of mechanical parts, a lot of connections, and they also try to make things pre-made, pre-sealed, pre-this, pre-that, to reduce the amount of error. And of course, reliability and functions are very, very huge things, and Bill can tell you a lot of stories about how things that get installed the wrong way. And that's why we see things that are sealed, we want you to play with it. We tested it, it's good, it's gonna work for this amount of years, and that's it. And bless you. And that's why we moved also from mechanical relays to electronic relays. The less moving parts, the more reliable that equipment is. I mean, think about your phone, your computer from the 90s with the hard drive that moves a lot before the solid state. And the transformer has a fan in it, and how unreliable that was. And now you can buy a computer that has solid state, consumes less energy, less probability of failure, because things do not move. Think about the VCR. How many moving parts was that? I thought, huh?
No, I'm kidding.
VCR, my friend, was an old machine that displays videos. So you put a cartridge there, and the amount of mechanics involved is so freaking intricate. It's sophisticated, it's awesome, but the possibility of something failing is very high. Like you have the tape a little bit looser than it's supposed to, and it gets caught up in there, and you pull on it and something gets broken. And so many gears in it, it's very, nice to watch, actually take the camera and watch that, but there's so many mechanics. Now, you can buy a DVD player, a Blu-ray player for 40 bucks and it will last for 10 years, no problems. Because there's less mechanical parts. So, think about that again. So, energy and power, heat and work, pressure versus flow, energy transformation, energy transport, and heat flow. And again, I always go back to the car example because the car is a very intricate part. Anybody have a car? Your car has a heating system, your car has an AC, your car has internal combustion, it does movement, it's very simplified. So if you can understand that in a way, you can understand a lot of things. If you can just look at the cooling and heating system in your car, that's a complete heating and cooling system in a small scale. So where does your car get the heat from? The engine. How does it get there? The radiator, the coolant. The coolant gets hot, goes into a small radiator, and air goes through it. That's why the car does not give you heat until it's hot. So in the winter, it's 0 degree outside, 32. You're gonna crank up the heat, you get nothing until the car gets hot first. The same coil will switch with the AC, and you have a small compressor that will cool the air, and you change that with the inside. So it's very simple. You have a sophisticated system that you can look at, similar what you're gonna do on a bigger scale in a house. Okay, what do we have? We have a few more constants here. We have, how many minutes? 15 minutes. You can do that. You can do a little bit. How do you feel like? You're good or do it Friday?
Friday.
Okay. All right.